I see someone is signed on. Can you hear me? You have to unmute yourself. Will the person who signed on unmute himself?
Thank you. Goodbye.
Brent, Christian, can you hear me?
Yeah, I can hear you.
And can you see the screen?
Yeah, I can.
Okay, thank you. Good morning. Welcome to EE 339. Can you guys hear me and see the screen?
Yes, definitely.
Okay, thank you. Perfect. I know it's very strange to have classes online, and it's very stressful for all of you. So I'll try to make the class as stress-free as possible. 339 isn't the easiest class in EE because there's a lot of physics involved, a little bit of chemistry. The math isn't that difficult. It's a lot simpler than 325, but the quantum mechanics that we use, some of the concepts are strange. You have electrons behaving both as a particle and a wave, and some of the concepts, frankly, can be a little bit confusing. You can have things like negative mass of particles and so on and so forth. But the math by itself is actually much simpler than in many of the other classes, okay? The textbook for the class is by Streetman and Banerjee, the 7th edition, the US version. Now, there's also international editions floating around. It turns out that the content of the chapters are pretty much the same, but the homework problems are different in the US edition and the international version. So if you bought a US international edition, overseas edition, that's fine. What you need to do is make Xerox copies of just the homework problems from the US edition, borrow one from a friend, because all the homework assignments are from the US edition. If you use other editions, the homeworks are different, okay? Hopefully all of you got a chance to maybe download the lecture notes and the course schedule. I'll upload everything under files. If you look at the course schedule, which is an abridged version of which is shown over here, what you'll see is for each lecture, I have reading assignments, and I think it'll be very helpful if you can do the reading out of the textbook, the relevant sections before class, because that way you can, I think, absorb the material better, and you can hopefully ask questions. The homework assignment shown in the course schedule are due on the dates shown, okay? However, if you have to, miss submission on that particular date, I'm willing to give you, a couple of days extra. But if you wait till the next class day, it'll be too late because I'll be posting the homework solutions also under files by the following lecture, and by then it'll be too late, okay? Now, I don't want you to be too worried about the homework because I've told the TA to grade the homework very liberally. It'll be almost treated like a completion grade, okay? So as long as you, make a halfway decent effort, you'll not be penalized much at all for numerical problems and things like that. But if you blow off the homework, of course, you'll get penalized. So each homework problem counts for 10 points, depending on the number of problems. Different homework sets range anywhere from 30 to, I think, 60 points, okay? So please try to do the homework, and please try not to copy the homework solutions from the internet, okay? Because I'm sure if you try a little bit, you can probably, download the solution manual and just copy it. Please don't do that because, as I've said, the homework grades really don't make much of an impact on the final grade, okay? What'll happen is, you may do well in the homework, but then, mess up in the exams. It's really the exams that matter in terms of the grades. In fact, I'm so liberal about homework. In past semesters, when we met face to face, I'd encourage students to work in teams. So I know it's going to be challenging during COVID, but if you want to hook up with friends and discuss homeworks with them, that's absolutely fine with me. But just simply don't copy the homework solutions, okay? Let's see what else. For the midterm, normally I allow one cheat sheet, both sides, 8.5 by 11, as well as copies of the formula that are given on the inside covers of the textbook, at least in the US edition. I'm not sure if the international edition also has those, okay? Now, because it's during COVID, I think I'll make it even more relaxed, and I think I'll probably make it open book, but I'll let you know for sure before the midterms, okay? But at least you'll get a chance to copy the homework, the formula on the inside covers, and make notes. Okay. I think the idea behind making notes is it sort of forces you to focus on what's most critical. Okay. And I think I'll still ask you to do that. And for now, let's assume that it will be closed book, but open notes and access to the formula that are on the inside covers of the book. Okay. For the final exam, you get one extra cheat sheet. Okay. And once again, the idea is kind of to force you to focus on what are the most critical concepts. All right. I know a lot of you are always concerned about grading. I tend to grade things fairly liberally. So pre-COVID, I typically hand out roughly a third A minuses, roughly a third Bs of different flavors. And then the remaining third would be mostly, various types of Cs. And I try hard not to flunk people unless, you absolutely bomb the exams, don't turn in the homework, and so on and so forth. Okay. I'll be probably even more liberal because of COVID. So, if you make a decent effort, do the homework and, do a reasonable job in the exams, don't worry. Even if your scores may be low, and ultimately I curve them. So, the final grades, I think you'll be very happy with them. Okay. I do make the exams quite difficult. And in terms of the numerical grading, I do grade them fairly tough. But then, when the final grades are assigned, I'm quite liberal. Okay. And I'll be especially liberal during COVID. Now, I've noticed that because this course is so dependent on, especially quantum mechanics, which is covered in the second chapter, which I call modern physics, people find that if you haven't done any quantum mechanics before, as I said, although the math isn't that difficult, the concepts can be strange, and a lot of people kind of give up hope and either drop the class or stop attending lectures and things like that. Try not to do that, because after you get over that hump in chapter 2, which is modern physics, and then a little bit of conceptual difficulty in chapter 3 and 4, which is after the midterm, where we apply these concepts of physics to how electrons move in a semiconductor. That's sort of the physicsy part of the class. And conceptually, that's also probably the harder part of the class. So if you can get over that hump, which is roughly up to the midterm, which will be at the end of chapter 4, which is optical generation, recombination, diffusion, things get a lot easier after the midterm, because the hard concepts are already taken care of. And then the second half is really the engineering part of the course, where you'll apply these concepts to all kinds of devices, okay, starting with p-n junction diodes, which I'm sure you've seen a little bit in 302. And if you've taken 438, you've probably seen a little bit of that. But in this class, we'll dive in a lot deeper and try to understand p-n junction physics in great depth. Okay, so we'll spend about 4 or 5 lectures on that. The reason is the p-n junctions are fundamental to many other devices, okay? And some of those will be discussed in the final chapter 8, which I call optoelectronics, where you'll see that depending on the way you bias a p-n junction, you get all kinds of fun device structures out of it. If you forward bias the thing, you get what is called a light emitting diode or a semiconductor laser. If you reverse bias it, you can detect photons. That's called a photodiode or a photodetector. If you shine radiation on it, such as sunlight, you can make a solar cell out of it. So the p-n junction, although it's a very simple structure, very, very useful. And then, of course, you can use the p-n junction in regular electronics, such as p-n junction rectifiers and so on and so forth. So I'll spend a lot of time on p-n junctions. I'll also spend a lot of time on chapter 6, which is field effect transistors, metal oxide semiconductor field effect transistors, because that is the workhorse of the semiconductor industry. 99% of the electronics that's on the market, and your microprocessor chips, different kinds of memory, they're all based on MOSFETs. In fact, something called CMOS, where you have a P-channel MOSFET and an N-channel MOSFET work hand in hand, okay? And hopefully you've had some introduction to these basic concepts in 302, and if you've taken 438, or I don't know if they talk about it in 411, but once again, we'll get into the physics a lot more in this class, okay? So chapter 5, which is PN junctions and MOSFETs, will pretty much take up 80% of our time after the midterms, okay? Which midterms will be right before the spring break. I don't spend a lot of time on chapters 7 and 8, which is bipolar transistors, because although the first transistor that was invented was actually the bipolar transistor, and for the next 20, 30 years, that was a dominant transistor technology. But because they consume more power than MOSFETs, bipolar transistors have kind of fallen out of favor, and they're really used in niche applications where you don't care about the power consumption, but you need very high speeds faster than MOSFETs. So you'll only really have a couple of lectures devoted to BJTs, although the physics is very interesting. But even here, it's really two PN junctions that are connected back to back. So the discussion about PN junctions will help with the BJT discussion also. And then that'll bring us to the final chapter on optoelectronics, where, as I said, it's basically PN junctions used in different ways, okay? Where you make lasers or light emitting diodes or photodetectors and so on and so forth. Honestly, I'll not be doing justice to optoelectronics. It's a huge topic. And if you're interested in the field, there's follow-up courses taught by Professor Seth Bank and others that you ought to take, okay? So we'll just basically give you a taste of optoelectronics. Let's see. I normally like to be interrupted during the lectures. So although you're muted, anytime you have your question, just unmute yourself and ask questions. I like questions. Now, I know it's a little bit awkward online through COVID and all that. So if you have questions anytime, with the official office hours are from 8 to 9. And the way I'd like to handle it is, you can, call me on my cell phone. I've given you my cell phone. It's 512-924-4799. Even during the lectures, if all of a sudden you can't hear me or you can't see the screen or something gets messed up, please text me on my cell phone and I'll try to take care of it, okay?
There actually is a question for you in the chat.
Oh, okay.
Yeah, sorry. I didn't want to interrupt you, but it's
Right.
reference to the cover formulas, because in the textbook, it's between pages 618 through 621 are the only ones I could find, but it's the semiconductor physics under that subcategory. Are those the ones you're referring to?
No, that's on the inside covers and the outside covers. So there's 4 pages of formula. Okay. And I think I've also made copies of those at the end of these lecture notes. So if you scroll to the end, you'll have those. Okay.
Okay, perfect. Thank you.
Yeah. And just unmute yourself and ask questions, because I have 2 screens and I don't always notice if there's questions on chat. Okay. Anyway, going back to office hours, although the office hours are from 8 to 9, and you can call me on my cell phone, I'd like you to feel comfortable to email me or call me at other times also. Don't call me at midnight on Friday, but any normal times, feel free to email me, text me, whatever. I'll try to be responsive, okay? My main office is not on the main campus. It's at the UT Pickle campus. So, hopefully as the semester rolls along, if the COVID situation improves, maybe we'll even go face-to-face, I don't know. Or if you want to come to the Pickle campus, we can meet face-to-face if you want to, if you have detailed questions. We'll figure it out, okay? So don't be bashful about contacting me, okay? Let's see what else. Yeah, I think those are the basics. All right, so let's jump in then. Any other questions at this point? All right, so these are the topics, as I said, that we cover, starting with crystal structure, okay? What I'll do today is basically introduce the topic, and I'll, throw in some concepts that I want to take my word for it. We'll, discuss all of these in gory detail as we go along. Oh, one more thing that I meant to say. So because it's being taught through Zoom, all the lectures are going to be recorded, and I'll post them on the cloud soon after the lectures. So in case if you sometimes miss the lectures, no worries, you can always listen to the Zoom lectures. And I think it'll be a lot more fun than Netflix videos. So I encourage you to listen to the Zoom lectures later on. But try to attend the lectures, because that way, if you have questions, you can interrupt me as you go along. All right. So what I'm showing over here are illustrations of what is known as Moore's law, that I'm pretty sure you've heard about, which was not really a law, but an economic observation made by Gordon Moore, who founded Intel Corporation. Okay. And what he noticed was, well, a little bit of historical note. The transistor was invented in 1947 by three physicists at Bell Labs, John Bardeen, Brattain, and Shockley. Those are individual transistors. But then in 1957 or 58, Jack Kilby at Texas Instruments in Dallas put them together to make integrated circuits. And that's really what launched the microelectronics revolution. Now, that also happens to be the year that I was born. So I brag to my friends that my birth launched the microelectronics revolution, but somehow nobody believes me. Anyway, so I was born the same year the integrated circuit was born. Okay. Gives you an idea of how old I am. Anyway, so the IC invention was a few years before 1960. And then pretty soon, the IC technology took off, and Gordon Moore noticed that every year the chips are getting more and more complex in the sense of number of transistors that industry was putting on the chips. Okay, and then what he did was, after a few years, I think around 1970 or so, he said, okay, let me plot the number of transistors on leading edge products as a function of time on a semi-log scale. So the vertical axis is not a linear scale, it's a logarithm of the number of transistors as a function of time. And he's sort of picking the most advanced IC at that time, okay? And he noticed something curious. So on the semi-log plot, as you can see, for these leading edge products, you get a straight line, which means that if this was a linear plot, that would be an exponential increase of the complexity of the chips, the number of transistors on the chip with time. Okay. That's why, if it's an exponential dependency, then if you take the semi-log, you get a straight line. Okay. Another way of saying the same thing is roughly every 18 months to 2 years, the number of transistors on leading edge chips seems to have doubled. Okay. And that trend, incredibly, has lasted over the last 50, 60 years, okay, till now. Okay. And then depending on the number of chips, people have given the technology different names. So if there's only a few hundred transistors, it's called SSI, meaning small scale integration. Then a few thousand, medium scale, large scale, very large scale. Then up to a few 100,000, it was ultra large scale. And then by the time you went to 1 billion transistors or so, that's called giga scale. Giga means 1 billion or more. And that's kind of where we are. Okay, so you're talking about 1 billion to several billion. And the joke is, the next era of IC technology will be called RLSI, ridiculously large scale integration. Okay. Now, how can you cram more and more of these transistors on a chip, which is typically about an inch or an inch by a side for these large complex microprocessor chips or semiconductor memory such as DRAM and SRAM and so on and so forth. But the main reason you can do that is that the sizes of individual transistors have been shrinking with time. Okay, and that's shown on the right-hand plot, where once again, I'm plotting it on a semi-log scale, where I'm plotting the log of the size, or the feature size. And what does that mean? Well, that's kind of a vague concept, but think of it as the channel length or the distance from the source to the drain of a MOSFET, or the gate length. Hopefully you've seen what a transistor looks like in other classes, but don't worry about the details. It's roughly the linear length scale of the transistor. You take the logarithm of that and you plot it as a function of time. And there also, Gordon Moore noticed that now the size shrinks with time. So you're able to put in more and more transistors on the chip, okay? So this basic principle is called scaling. You scale the linear dimensions of the transistor from one generation to the next. And that's why you can cram in more and more transistors on a chip, okay? And if you look at these numbers, in this case, they're plotted for DRAM, dynamic random access memory, okay? Now, before I joined UT in 1987, I used to work at Texas Instruments, and our team developed the world's first 4 megabit DRAM, okay? And I was excited about that because, you know, that's the size of memory which could contain all the text, for example, in the Streetman Banerjee textbook. So that kind of gives you an idea that, you know, how much information content you can have in a 4 megabit DRAM, okay? But of course, that's ancient history by now. And now you're up to, you know, gigabit, multi-gigabit DRAMs, okay? Now, if you look at the right-hand side, you'll see the sizes of objects such as blood cells, okay? Now, those are humongous compared to the sizes of transistors that we have today, okay? Just for calibration, leading edge transistors today made by companies like Intel or Samsung or TSMC have dimensions of the order of 7 nanometers. A nanometer is a billionth of a meter, okay? And in fact, by the time you go down to dimensions of less than, you know, 100 nanometers or so, that area of technology is called nanotechnology, okay? Now, by the time you go into nanotechnology, notice that the transistor sizes are smaller than the sizes of bacteria, and in fact, approaching the dimensions of viruses. So that tells you, you know, how tiny these transistors are, okay? I guess it'll be interesting to plot the coronavirus on this chart and see what the length scale is of the coronavirus. Now, on the top right-hand side, I show a photograph of an Intel microprocessor chip where you remove the top cover. And if you look at it, you can clearly see different colors on the chip, right? Now, that's not because Intel Corporation made the chip and then painted certain regions purple or blue or whatever. It's because the dimensions of the transistors are so small, they're smaller than the wavelength of ordinary light. So when light shines on this transistor, it's kind of like a diffraction grating, okay? So depending on the periodicity of the structures, different wavelengths of white light diffract by different angles, and that's why you see these different colors, okay? Okay, and interestingly enough, just as an aside, if you look at the colors on the wings of a butterfly, in many cases, it's also because of this diffraction phenomena. It's not because of pigments on the wings of a butterfly. The butterfly wings have these tiny structures. These are sometimes called photonic crystals, so that when white light shines on the wings of a butterfly, different wavelengths will bend by different angles, and that's why you see beautiful colors. And it's the same physics over here. Now, why do I mention that? I mention that because that also poses a huge challenge in terms of manufacturing of these chips, because we'll see later on that when you make them, you have to use photographic techniques called lithography, where you shine ultraviolet light through glass masks, which have transparent regions through which the light can shine onto the wafer that I'm processing, and dark regions where the light is blocked. And these patterns correspond to the circuits I try to build, okay? Now, because the dimensions are so small, that when I shine light through this mask, the light will bend in strange ways because of diffraction phenomena, which makes manufacturing these so challenging, okay? Now, I don't really discuss manufacturing to a great degree in this class. There's a follow-up class that I teach, E440, in fact, right after 339, where we get into the depths of manufacturing issues and all kinds of interesting physics over there also. Now, I'll touch upon that a little bit here and there, especially at the beginning of chapter 5, where I'll give you a rough overview of how chips are made. Also, at some point, when I met face-to-face, I would show students a cool video called Silicon Run. Now, because we are not meeting face-to-face, I'll give you a link of a URL link on YouTube where you can look at this video. It's a cool video which shows how these chips are made, okay? Okay, so the devices that we'll be focusing on are made on semiconductors, and in fact, in most cases on single crystal semiconductors. That's why in chapter 1, we look at what a crystal means. They're made in single crystal semiconductors because that's what gives you the highest performance transistors or semiconductor devices. You can make them in non-crystalline materials, but then the performance suffers, okay? So the question, of course, is, what the heck exactly is a semiconductor, okay? Well, one way of looking at it is in terms of the conductivity of the material, which is sometimes indicated as the Greek symbol sigma, which is the reciprocal of the resistivity rho, which is shown over here, okay? So a semiconductor, as the term implies, has a conductivity, or the reciprocal of that, which is the resistivity rho, which is intermediate between that of a poor conductor, such as an insulator, such as glass. And of course, if it's a poor conductor, the reciprocal of that would have a high resistivity of 10 to the power 10 ohms in this particular example, or a very good conductor with a low resistivity, things like metals, okay? So that's why a semiconductor is called a semiconductor. It's a conductor, but not as good a conductor as a metal, but a better conductor than an insulator. That, of course, doesn't really give you a real sense as to why the semiconductors are so useful from an engineering point of view, okay? To understand that, you have to look at some of the attributes of the semiconductors, which are shown over here. I'm just showing some of the key attributes, okay? And let's take a quick look at it, okay? Now, to understand these properties, we have to understand something called the energy band diagram of semiconductors, which I'll be discussing in gory detail in chapter 3, and we'll be using band diagrams to basically study every single device. Okay, this is just a preview, okay? So just as an introductory concept, when I talk about a band diagram, I talk about energy levels that electron can have in a semiconducting crystal. So this is electron energy plotted on the vertical scale as a function of position in that semiconductor device. Okay, so think of a transistor. At every location, I can plot what the electron energies are as a function of position. All right. Now, what you'll find in chapter 2, 3, 4, and so on and so forth, that electrons in a semiconductor cannot have any arbitrary energy level. They're only allowed to have certain ranges of energies, which are called energy bands. And the one down below is called the valence band. This corresponds to the valence shell of atoms in the crystal. In our case, it'll be the silicon crystal. The top of the valence band is called E sub V. And then above that, you'll have a more or less empty band, which is called the conduction band. It's normally empty except for a few electrons being in there. And the bottom of that is called EC. And the separation between the two is called the energy gap, okay? And once again, just take my word for all of these. Like I said, I'll be proving all of this later on, okay? I just wanted to show you this concept of allowed energy levels, energy bands, forbidden energy levels, which is called the energy gap. So electrons in a solid cannot have energies in this range, but then they can have energies above that in this conduction band, which is normally going to be more or less empty, okay? More or less, not exactly. The valence band is going to be full, almost completely full, but not completely, okay? And we can use this picture to understand some of these properties over here, okay? So let's look at the first one, which is how the conductivity changes with temperature, capital T over here, okay? One finds in a pure semiconductor, the conductivity is a strong exponential function of temperature. It varies as exponential, e to the power minus a constant, which is this energy gap that I just showed a second ago. Okay, so that's my EG. That's what I call EG, okay? Divided by 2 kT, K being the Boltzmann constant, and T is temperature in Kelvin. So in this class, of course, in all science classes, you always measure temperature in Kelvin. So if you have temperature in centigrade, you have to add 273 degrees to that, okay? So what this tells you is, if my temperature is very low, say close to absolute zero, the conductivity is going to be very, very small, or the reciprocal of that, the resistivity is going to be very, very large. So a semiconductor will behave like an insulator. So it turns out, if the temperature is very, very low, this valence band will be completely filled up with electrons, and the conduction band will be totally empty. And that can be used to understand why such a material will be an insulator. If you apply electric field to it, it will not conduct current. Let's see if you can understand that based on a simple analogy. And the analogy that I use is, you can think of these bands as bottles of water. Okay, so now in the valence band, I have a water bottle that is completely filled up with water, while the conduction band is another water bottle that is empty. Okay, now if I ask you the question, what would be the net transport of water from one end of the bottle to the other if I tilt it in the gravitational field? I take a bottle, in one case totally empty, that's my conduction band, and another case completely full, that's my valence band, and I sort of jiggle it around, and I ask myself, what will be the net motion of these water molecules from one end of the bottle to the other? Now, if it's a completely empty bottle, that's almost like a silly question, right? I mean, if there's no water, obviously there'll be no transport of water, okay? Similarly, in a completely empty conduction band, which has no electrons in it, even if you apply electric field, there'll be no transport of electrons or electrical current. The trickier part is the valence band, okay? Because if I think that, I have the valence band full of electrons, and surely if I apply electric field by dropping a voltage across a device, those electrons should move, and that should give rise to a current, right? But think of this water bottle analogy. If I have a completely full bottle and I move it around, yeah, sure, water molecules can move from one end to the other, but that will dislodge other molecules. And once again, there will be no net transport of water, right? So similarly, if it's a completely full energy band, the electrons in this band cannot gain energy from the electric field and move up, because if they try to move up, they get into this energy gap, which by the rules of quantum mechanics are forbidden. Okay, electrons cannot have energies in that energy gap. That's why a completely full band, completely full valence band also does not give rise to current. On the other hand, if I now raise the temperature T, what's going to happen is the electrons in this valence band start jiggling around. They have more and more of a thermal motion. And if the temperature is high enough, a few of these electrons will get thermally excited from the valence band into the conduction band and create a few negative electrons and leave behind a few empty states, which are called holes, which you'll see behave like positively charged carriers. Okay, so I excite a few electrons. In the conduction band, those behave like negative charged particles, which electrons are. And interestingly, what's left behind behave like positively charged particles. Those are called holes, because I've removed electrons from those quantum states. Going back to our water bottle analogy, what am I talking about? So now in my empty bottle, I'm introducing a few droplets of water. And surely now in the gravitational field, those water droplets would move down, right? Conversely, in this full water bottle, if I've removed a few droplets of water, I've created bubbles, right? And the bubbles would move in the opposite direction. So while the water droplets move down under gravity, the bubbles move up, right? Similarly, it turns out the electron energy points vertically upwards, while the hole energy increases downwards. So you can think of the holes as the analog of these bubbles and the electrons as the analog of water droplets. Now, mind you, these are analogies, so don't push these analogies too far. This just to get a sense of why it is this way. Now, let me ask you, if I keep increasing the temperature, do you think the number of these electrons and holes would increase, decrease, or stay the same? If anybody wants to answer, you can unmute yourself. Sorry?
Increase?
It'll increase. Yeah, very good. It'll increase. In fact, it'll increase exponentially. So you have exponentially increasing numbers of electrons and holes. That's why the conductivity increases, okay? So this gives you one potential application of a semiconductor, which would be a thermometer. So you can just take a bar of a semiconductor, apply a voltage to it, And as you heat it up, okay, it becomes more and more conductive, and that would show up as an ammeter current, for example, okay? Very similarly, if you look at property number 3, the conductivity also increases with electromagnetic radiation. Okay, so if I now shine electromagnetic radiation on the semiconductor, the conductivity can also increase, provided it's the right color of radiation. Now, you may have seen in your modern physics classes in high school or hopefully at UT that electromagnetic radiation has a wave type property, but it also has a particle type behavior. And these particles of light are called photons, where the energy of a single photon is given by something called the Planck constant h divided by the frequency of the photon nu, where the frequency of the photon times the wavelength of the photon gives you the speed of light. Remember that from your physics class? So if you look at light in the visible range, visible red light has a relatively long wavelength of 800 nanometers and a corresponding frequency. The product of the wavelength and the frequency is a constant. So as the wavelength increases, the frequency goes down, meaning that the photon energies go down. On the other hand, shorter the wavelength, when you go towards the blue end of the spectrum or the ultraviolet part of the spectrum, wavelength is going to reduce, frequency increases, and therefore the photon energy of a blue photon will be more than the photon energy of a red photon. All right. So going back to my band diagram, if I now shine photons with an energy h nu greater than this band gap, what's going to happen? Well, the same thing that happens with high temperatures. A few electrons will be excited from the valence to the conduction band. More photons I shine, more of these electron hole pairs are created, and the conductivity of the semiconductor increases. Okay, so this could also be the basis of a simple device, which is a photodiode or a photodetector. So this is my electromagnetic radiation shining on this photodiode. Okay, and then I can bias it and have an ammeter hooked up to it. And this, in fact, is a kind of device that you have in your garage door openers. Okay, if you look at your garage door opener at home, you'll see at the very bottom, you'll have a laser at one end, and at the other end that you can't really see is a photodiode. And the way it works is, if you stand in the path of the garage door opener, you'll be interrupting this light source. The resistance of the photodiode would increase, and that will prevent the garage door opener from coming down. So very simple devices, okay, based on photodiodes. Now, for these photons to be absorbed, however, you have to have a photon energy h nu greater than or equal to the band gap. Because if not, what's going to happen? Electron in the valence band would try to absorb the photon, say with a lower energy, but there's no allowed states in the band gap, right? So then it would just fall down and the photon would not be absorbed. This, in fact, is a simple explanation of why different solids have different colors. So if you look at an insulator such as glass, that has a very large band gap of 9 electron volts, okay? By the way, in this class, we'll be measuring energies either in joules, but very often in electron volt units, where 1 electron volt is the energy an electron gains by going through a potential difference of 1 volt, okay? And that's a very convenient measure of energy because, you'll be applying, I don't know, maybe 3.3 volts to a transistor, right? So immediately you know that the energy that the electron could gain would be 3.3 electron volts, all right? But sometimes you'll have to convert them to other MKS units, and the conversion would involve multiplying electron volts by the charge of the electron, which is 1.6 times 10 to the minus 19 coulombs, and that will give you energy in joules. Just for calibration, the band gap of silicon, which is one of the most common semiconductors, is 1.1 eV, while the band gap of a metal by definition is 0 eV, right? So let's see what's going to happen if I shine light through glass or an insulator, which has a very large band gap. Now, photon energies in the visible part of the spectrum have energies of the order of roughly electron volts or so, okay, depending on whether it's blue or red, okay? Now, what would happen, do you think, if I shine visible light through glass? Would any of those photons be absorbed?
No.
No, just pass
No.
right through.
Exactly. That's why glass is transparent, okay? On the other hand, if I shine photons into metal, which has a zero band gap, would they be absorbed? Yeah, they'd be absorbed, right? That's why a metal is opaque. Now, of course, different metals have different colors, which are due to other physics that I'll discuss in passing later on, okay? But the more interesting part is semiconductors, where I may choose a semiconductor with a band gap which is right in the middle of the electromagnetic spectrum. So if I look at the electromagnetic spectrum as a function of frequency, okay, this might be the blue part and this might be the red part of the spectrum, okay? The corresponding energies are h nu. And suppose I choose a semiconductor which has a band gap somewhere in the middle. Let's see what the color of that semiconductor should be. That semiconductor, would that absorb or transmit the blue photons?
It would absorb them because they have an energy greater than that of the band gap.
Excellent. On the other hand, the red photons would not be absorbed. So if I take a semiconductor like that and I hold it up against white light, that semiconductor will look red because the red colors will be transmitted through, okay? Now, silicon, on the other hand, is a band gap where all these wavelengths are absorbed. So that's why a piece of silicon looks opaque. On the other hand, if you go to even shorter, lower frequencies, which is in the infrared, which is heat radiation, that does pass through a piece of silicon, okay? The next property is electrons. There's two types of charge carriers in a semiconductor, as I just mentioned. You have the negative electrons, but then the missing electronic states behave like positively charged carriers called holes. And that can be the basis of very interesting physics in PN junction diodes or bipolar junction transistors or all these optoelectronic devices. So for example, we'll see in chapter 8 that not only can you absorb photons and create electron hole pairs in a photodiode, you can also bias a PN junction, inject electrons and holes, and if these electrons recombine with the holes, they'll give off light, and that's what you have in a light emitting diode or a laser, okay? Now, as I said, the semiconducting materials can be in different states, such as single crystal, which I'll be discussing in just a second, but they can also be in non-crystalline states, such as liquids, random arrangement of the atoms called amorphous solids, and so on and so forth. Some of them are in organic materials. So semiconductors can be found in different states of matter, but in this class, we'll be focused primarily on the single crystal semiconductors, things like silicon or gallium arsenide, because that's what all the high performance devices are made in, okay? Plus, if it's a single crystal solid, you have a nice periodic arrangement of the atoms, so the mathematics becomes a lot easier, okay? Because if you have a periodic arrangement of atoms in space, you can take the Fourier transform of that. Just like if you have a periodic signal, you can take the Fourier transform and you get discrete frequencies. Similarly, we'll see in a crystal, you can take Fourier transforms in the space domain and you get nice frequency components in what's called reciprocal space. But I'm getting ahead of myself over here. Okay, now I have saved the most important property of semiconductors, number 2, for last, and that is the conductivity of the semiconductors can be engineered over orders and orders of magnitude by adding trace amounts of impurities called dopants. You can do that with insulators. They're always crummy conductors. You can do that with metals. They're always excellent conductors. But on the other hand, with semiconductors, depending on the number of these impurities that you intentionally engineer in, you can make the semiconductor more conducting or less conducting. The more of these impurities that you put in, it gradually becomes more and more conducting, okay? And that's in fact how all semiconductor devices are made. You inject these impurities just at the right levels, right concentrations at right depths to make all these devices, transistors, diodes, or whatever, okay? And we'll discuss that, how that's done in chapter 5, the manufacturing aspects of it. Now, how does the physics of that work? Why do these impurities change the conductivity, and what kind of impurities am I talking about? see that, let's go to the periodic table, which I'm showing in the next slide. Now, this is not the entire periodic table. I'm just zooming in on the part of the periodic table which is relevant for semiconductor physics. And I want you to focus on column 4 of the periodic table, where you have the most common semiconductor, silicon. Okay. Now, I don't know if you remember from your freshman chemistry classes what the columns in a periodic table refer to, but basically it is the number of electrons in the valence shell of an atom, the outermost shell of an atom. So in the case of silicon, we'll see that you have a core which is made up of a certain number of protons, 14 protons, and anywhere from 14 to 16 neutrons. So you have 14 protons in the nucleus, and let's say 14 neutrons, depending on the isotope. So this would be silicon isotope 28. And then the various electrons lie in these different Bohr orbits that you may remember, right? So you have 2 of them in the so-called first shell. And once again, I'll get into the details starting in chapter 2 when you look at basics of modern physics. Hopefully you have seen this in your chemistry class, and this is just a refresher, okay? So you have 2 electrons in the first core shell. Then you'll have 8 electrons in the second shell between 2s and 2p. But then the interesting stuff happens from a chemistry point of view or semiconductor physics point of view in the outermost shell, the third shell, 3s and 3p. By the way, these are my versions of circles, so I'm taking some creative license. So these are all circles, okay? So it turns out you have 2 electrons in the 3s shell and 2 electrons in the 3p shell. Okay, now if you add them all up, it adds up to 14. So you got 2 plus 2, 4 plus 6, 10, and then 4 electrons in the outermost valence shell. Okay, so the other thing that you hopefully remember from your chemistry class or modern physics class is atoms like to have an outermost shell which is complete in the sense that they want to have the outermost shell filled up with up to 8 electrons typically. Okay, now clearly that's not the case in the case of silicon. It only has 4 electrons. So the way silicon forms a crystal is each silicon atom likes to surround itself with 4 silicon atoms, okay, and form 4 so-called covalent bonds, okay, where each of these bonds has 2 electrons. So that now with 4 covalent bonds, you end up with 8 electrons on average surrounding this silicon atom. Now, how do you get the 8 electrons? So you got the 4 that the silicon atom itself had, then it borrows, if you will, the second electron from each of these 4 neighboring silicon atoms. And the network continues like that. So this is surrounded by 4 nearest neighbors and so on and so forth, okay? And that's how this entire crystal structure continues. That crystal structure, by the way, is known as a diamond structure, okay? It's called the diamond structure because if instead of silicon atoms, these were made up of carbon atoms, that's exactly what diamond is, okay? You know, silicon has the same kind of structure. That's why it's called the diamond structure, all right? Now, if you have all these covalent bonds satisfied, that semiconductor will not conduct electricity, because going back to our earlier picture of energy bands, that is the situation where you have the valence band corresponding to these energy levels of this outermost valence shell completely filled up with electrons, okay? And the conduction band completely empty. On the other hand, this process of exciting carriers from the valence to the conduction band, creating conduction electrons and leaving behind these positive holes, corresponds to breaking some of these bonds. And if you break a bond, you end up getting this negative electron, which moves opposite to electric field. And what's left behind acts as this positive hole, which would move in the direction of the electric field. So if I apply the electric field in this direction, because electrons have a negative charge, they move in this direction, while the holes would move in this direction, okay? Or if I shine photons on it, H nu greater than the band gap, once again, it would break some of these bonds, and that's how you increase the conductivity. In this case, it's called photoconductivity of the solid, okay? So if all these covalent bonds are intact, that's a filled up valence band and an empty conduction band. And anytime I break some of these bonds, that corresponds to excitation of carriers from the valence to the conduction band. Okay. Now, this picture can also be used to understand this concept of doping that I mentioned a minute ago. Okay. I said you can dope a semiconductor with impurities. Now, when you hear the term impurity, I mean, that seems to imply that, oh gosh, if it's impurity, it's got to be bad. No, you can have bad impurities, but in this case, you can engineer the right kind of impurities to change the electronic properties properly. Okay, so what do I mean by that? Well, in the case of silicon, which once again is the most common semiconductor, you can put in impurities from column 5 of the periodic table. Now, if it's column 5, can anyone tell me how many electrons a phosphorus atom or an arsenic atom would have in the outermost valence shell?
5.
Excellent. Okay, so let's see if I replace the silicon atom with, say, a phosphorus atom. What's going to happen? Well, it's got 5 electrons. 4 of those would go towards meeting these 4 covalent bonds, but then the 5th one has nowhere to fit, right? So that is then going to act as this conduction electron, okay, that can roam around in the direction opposite to the electric field. You can also do that with arsenic or antimony. What does that correspond to in the band picture? Well, a moment ago, I told you that in a perfect semiconductor, you have these allowed states that are filled up in the valence band. The empty states are mostly empty states in the conduction band, but then the energy gap where you have no allowed energy states for the electron, right? But it turns out that's true only if it's a perfect, pure, defect-free semiconductor. If I intentionally introduce these impurities, then all bets are off. And in the case of this column 5 impurities, which are called donor type impurities, they introduce energy levels close to the conduction band, okay? That energy separation is so small compared to the thermal energy, which is called KT. This quantity KT, by the way, is known as the thermal energy of the electrons, okay? And at room temperature is 300 Kelvin. This quantity is 25 milli electron volts, approximately, okay? The band gap is 1 electron volt. So the thermal energy is 25 milli electron volts, which is much smaller than the band gap. That's why if you plug in these numbers, you don't really excite a lot of carriers, but you do excite some. On the other hand, if I introduce energy levels close to the minimum of the conduction band by introducing these donor type impurities, this column 5 impurities, that energy separation is much, much smaller, of the order of maybe 50 milli electron volts. So this 5th electron in the donor impurity can be very easily excited into the conduction band. And that process is called donation of electrons to the crystal. And that's why these are called donor type impurities, okay? And if you obviously put in more and more of these donor type impurities per unit volume, you can make the material more and more conductive. If you have fewer concentration of these donor type impurities, you have fewer electrons, it's going to be less conductive semiconductor, more resistive. Okay.
Is there a minimum like energy difference you can reduce those bands to? Or is it just dependent on what
Are you talking about this band gap or?
Yeah, like if you put in a bunch of impurities,
Right.
and try to make it as conductive as possible, let's say.
Right. That's a very good
Is there
question.
like a point where they would be almost connected to each other, or?
Excellent question. Yeah. So what you're asking is, what happens if I add not just a few of these phosphorus impurities or arsenic impurities, but I have a whole bunch of them, right? So what would happen then is these impurities would start interacting with each other, and they themselves would form a band. And at some point, these would merge with this conduction band. And at that point, the semiconductor would almost look like a metal, okay? But you're talking about very, very high doping concentrations. And generally speaking, you don't really dope semiconductors that heavily, but sometimes you could. That's a very good question, yeah.
Okay, thank you.
Sure. All right, so I talked about donor type impurities, which are based on column 5. You can have the same kind of physics by putting in column 3 impurities, such as boron. Now, column 3 means I have 3 electrons in the valence band. So if I put in a boron, what's going to happen? I want to have these 4 covalent bonds, so I can satisfy 3 of them. But when it comes to the 4th one, there's a missing electron. What's that going to act as? Electron or a hole?
Electron hole. like a positively charged hole.
Right. So it's called a hole. You don't call it electron hole. So if it's electron, it's negatively charged, and a missing electron is called a hole. You're right. So it's going to be a hole. In terms of the energy band diagram, now we introduce energy levels close to the valence band. You can easily excite electrons from the valence band to these. These are called acceptors because they can accept electrons from the crystal. And in the process, it creates these positive holes. Okay. And if you have a p-type dope region, positively doped region, right next to an n-type dope region, that's what you get in a p-n junction. All right. Let's see. Any questions? All right. So I've kind of given an idea of how we can change the electronic properties in a very carefully controlled fashion and make a semiconductor more and more negatively doped. That's why it's called an n-type semiconductor, or p-type doped, or positively doped by putting in column 3 impurities. Okay. Now, from this part of the periodic table, you can also see how you can make other types of more complicated semiconductors. So if I'm just in column 4, based on elements, those are called the elemental semiconductors, but you can also make compounds symmetrically around column 4 to make all kinds of interesting semiconductors, such as gallium arsenide. That's a very common semiconductor that's used a lot in optoelectronics. How does that work? Well, if I take a gallium atom, how many electrons does the valence shell have in gallium?
3.
Very good. So in this case, I'll surround it with 4 arsenic atoms. Arsenics have 5. So the 3 plus 5 add up to this magic number of 8, right? So now, once again, you get these covalent bonds. But because they're not identical atoms, the bonds also are partly ionic in character. In fact, the most extreme example of that is, say, sodium chloride, which is not shown in this part of the periodic table. But sodium is in column 1 of the periodic table, so it has 1 electron. Chlorine, which is in column 7, has 7. So in sodium chloride, this single electron transfers over to the chlorine, creating a sodium plus and a chlorine minus, and then you get Coulombic interactions by forming ionic bonds. Gallium arsenide isn't quite as extreme as that, but it's kind of a mix of a purely covalent bond type character, as in silicon or germanium or diamond, but partly ionic character, as in sodium chloride. Okay. You can have other combinations also. So you can have things like all kinds of interesting combinations like aluminum phosphide or aluminum antimonide or indium phosphide. Okay. Or you can go 2 steps further. So you can have a column 2 with 2 electrons reacting with a column 6. So you have things like zinc selenide, zinc sulfide, and so on and so forth. Okay. And all of these have different band gaps, different lattice structures, and so on and so forth. Okay. So these lattice structures for these compound semiconductors have obviously 2 types of electrons in the crystal, unlike something like silicon or diamond, which is the same kind of atom everywhere, right? If it's the same kind of atom everywhere, those are sometimes called diamond structures, because that's what diamond is. It's all carbon atoms. But if it's 2 different types of elements, such as 3,5 or 2,6, and so on and so forth, those are called zinc blende structures. Okay, because zinc blende is a mineral in nature. I believe that's I think zinc selenide. I think that's a mineral in nature. As you go along, we'll see that because of these electronic properties, silicon is wonderful for electronic applications such as transistors, but unfortunately, it's not very effective in terms of absorbing or emitting photons. I'll get into the details in chapter 4. That's why many optoelectronic devices are made in things like gallium arsenide or other compounds. You can also mix and match these elements to make more complicated compounds. And examples of these are, say, ternary alloys. Ternary means 3, quaternary means 4. So in this case, you can say, let's take a quaternary alloy. So in this case, what you can do is, instead of, say, aluminum arsenide or gallium arsenide, you can mix in 2 parts of column 3 elements, a little bit of aluminum with a little bit of gallium. So a fraction of, say, I don't know, 30% aluminum, 70% gallium. And then on the other side, maybe 60% arsenic, 40% phosphorus. Okay, and you can vary those. And we'll see in chapter 4 and then in chapter 8, when you talk about optoelectronics, by having these complicated alloys, you can tune the band gap over different ranges. Now, why do you think that would be useful and interesting from an optoelectronics point of view? To answer that, let's go back to this electromagnetic part of the spectrum. And remember, I said that if my band gap is over here, it would absorb these higher energy photons, but transmit these photons, right? So here, if I'm looking at these ternary and quaternary semiconductors and I engineer the band gap, what's going to happen to the color of the semiconductors? It'll change, right? So you can engineer the minimum photon energy that you can absorb. Or conversely, if I make a LED, a light emitting diode, or a laser, what's going to happen to the color of the photons that come out as I change the band gap? It'll change, right? So if I make the band gap of these alloys more towards higher energies, you might get blue photons coming out of it, right? If I decrease the band gap by working with these different alloy compositions, I might get more in the red part of the spectrum. Okay, so you can get different colors of lasers and LEDs out of it. And like I said, we'll discuss a lot of that in chapter 8. Any questions? All right. So I've tried to give you sort of the grand picture. And like I said, I'll discuss all of these in gory detail as we go along, but I wanted to have a rough sense of what we're going to discuss in this class. So next, what I want to do is then start discussing this concept of crystals and crystal structure. So if you look at solids and you look at the arrangement of the atoms in the solid in space, you can broadly speaking put them into 3 categories. So assuming these dots are atoms, on the left-hand side, you see that the atoms have a nice periodic arrangement in space. It's making a more or less a square array. And if this continues over the entire solid, those are called crystalline or single crystal solids. And that's, once again, what we'll be focusing on this class, because that's the kind of semiconductor structure which gives you the best electronic properties. And you can kind of hopefully see in a rough sense, because now if I move electrons or holes in this very organized periodic arrangement, hopefully they can travel unimpeded more easily. On the other hand, if these atoms don't have any periodicity in space, they sort of put in random order, that's called an amorphous solid. So now if I try to move electron in there, we'll discuss this in detail in chapter 3 and 4. But hopefully intuitively you can see that the atoms would be impeded, the electron or the whole motion would be impeded a lot more. Therefore, the electronic properties would be inferior. Okay. Now, somewhere in between, you have what are called polycrystalline solids. Here you have short range order of the atoms. Now here I'm not showing the actual atoms themselves, but I'm showing these planes of atoms. So when I look at a plane like this, think of this as an arrangement of atoms, if you will. Okay. So in this case, what I'm trying to show is these atoms have periodic arrangement over a short distance. These are called grains, but the neighboring grains have a different periodic arrangement. Okay. And the boundary between them is a defect. It's called a grain boundary. Okay. So it's not quite as random as amorphous, but not periodic over the entire structure as single crystal. Okay. Now it turns out, although we'll be focusing mostly on single crystal materials, because the semiconductors such as silicon or gallium arsenide that we'll be using are going to be single crystal, in an IC, you actually make use of all 3 categories of solids. So we'll see that on top of, say, a silicon channel, to make a transistor, you have to grow an insulator such as silicon dioxide. And that silicon dioxide is generally going to be an amorphous solid. That's a glass and insulator. Okay, those are amorphous solids. On top of the insulator, the so-called gate insulator, you put in a structure, which is called the gate electrode. You may have seen this in other classes. So you have a source, drain, you make an insulator, and then you put a gate on top. This gate itself is made up of a metal or polycrystalline solids. Okay, so you do make use of all 3 categories, but all the fun stuff in the channel is made up of highly periodic arrangement of these atoms, single crystal solids. Okay, so that's what I want to discuss. I guess I'll start off today, but then we'll discuss that more on Monday. All right, so how does one describe a crystal mathematically? You describe it by introducing a mathematical concept called a lattice. What is a lattice? A lattice is an infinite periodic arrangement of points in space. So there's no physical entity that I'm talking about. It's just an array of points where it is a symmetry that determines the lattice, not the magnitude of the distances between them. Okay, so a simple example would be, if I'm looking at a one-dimensional problem, a lattice would be uniformly spaced points. Okay, and it doesn't matter if the distance between these points is 1 angstrom or 1 mile or 1 light year. You just have one possibility. Okay, in 1D you only have one possible lattice. Okay, uniformly spaced points, because that's the only symmetry that I'm talking about. On the other hand, in 2D, as in these examples, so this is a case where I have a square lattice. It's kind of like a square, right? And it doesn't matter if the sides of the square are 2 centimeters or 15 meters, and it's the same square type of symmetry. So there's only one type of square lattice. Okay. On the other hand, you could have an arrangement of the points which is more like a rectangle, right? So now this distance is not equal to this distance, right? There's a square and a rectangle have the same symmetry. Well, a square is a special case of a rectangle, right? Where the two sides A and B are the same, but you have to agree that a square has additional symmetry over and above a rectangle, right? So in a square, I'm putting A equal to B, while in a rectangle, A and B are not equal to each other, right? So anytime I have additional symmetries, a square being more symmetric than a rectangle, I call it a different type of lattice. So this is a square lattice, and that would be an example of a rectangular lattice. It turns out in 2D, there are 5 different types of symmetries that you can have, 5 and no more. Okay. In 4D, in 3D, it turns out there's only 14 different types of symmetries that you can have. Okay. And these are known as Bravais lattices. Bravais was a French physicist who first worked out all the possible symmetries. Okay. So once again, it's a symmetry that matters, not the actual dimensions between the lattice points. And up to now, it's just a mathematical construct. Okay. So I'm not looking at something that you can hold in your hands. Now, at each of these lattice points, then you can put in something physical, such as an atom. So these dots could be silicon atoms, for example. I mean, a silicon atom doesn't really have a square lattice, but just hypothetically, it's some kind of an atom, say, right? And the physical entity that you put in is what's called a basis. And when you do that, you end up with what's called a crystal. So you first construct this mathematical arrangement of points in space, periodic arrangement, and then at each of these lattice points, you put in an atom, which is called a basis, and that's how you end up with a crystal. Now, what makes life a little bit complicated is this basis may be a single atom, as shown in this example, or it could be a group of atoms. So you could have a scenario where each of these dots might correspond to not just one atom. You may have an atom at this point and maybe another atom in this direction, okay? But if you do that, then you have to do the same thing at every lattice point. So here, I put one atom, and the second atom maybe have a slightly different flavor. So this could be now, the first atom, the dots might be these gallium atoms, and these crosses might be arsenic atoms. So arsenic, gallium. So at each of these lattice points, where the lattice points are shown by these black dots, I now have a basis of 2 atoms, say a gallium and an arsenic, okay? And that's very often going to be the case in this class, okay? And that makes life a little bit more complicated, because now things can be confusing, because if I now look at the arrangement of the atoms themselves, you might say that, hey, it's not really quite symmetric. This distance is different from that distance, right? So you have to kind of, strip away this concept of the basis put on the lattice points, okay? And as we go along, hopefully it'll become a lot more clearer. So To summarize this slide, a crystal has long range order. A polycrystalline material has short range but no long range order, while an amorphous material has no long or short range order. All right, let's go back to the mathematical definition a little bit more and still stick with two-dimensional lattices. Now, we have a slightly different arrangement of the lattice points. It's not a square or a rectangle, but this now forms a rhombus, right? And the simple example of that is, see this rhombus, which is shown in blue, ODEF, where the dimensions of these edges A and B have been chosen to be different to each other. B is clearly larger than A. And this angle, say alpha, is not 90 degrees, as we had in the previous example of the square or the rectangle. Now, in some sense, a square or a rectangle are special cases of a rhombus, right? So in this rhombus, if I made A and B equal to each other and alpha, so here it's not equal to 90 degrees, sorry. So if this alpha was forced to be 90 degrees, a rhombus looks like a rectangle, right? But surely you have to agree that a rectangle is more symmetric than a rhombus, and a square is even more symmetric than a rectangle, right? So each time you have additional symmetries, you call it a different kind of a lattice. And that's not just a matter of nomenclature. It turns out that has very, very interesting implications for the electronic and the optical properties, as we'll discuss, okay? So it's not just for the sake of definition that we call them different lattices. It has real physical and engineering consequences, okay? Now, when it comes to this, in this case, this is a rhombic lattice, okay? You want to have a nice, compact mathematical way of describing the lattice, because then every time I give you a problem, surely you don't want to have to, plot these points in the arrangement of a rhombus. In fact, you need to do that over all space, right? Because remember, a lattice is an infinite arrangement of atoms in space. You certainly don't want to do that. If you want to do calculations, you don't want to have to draw an infinite arrangement of atoms. You want a more compact way of describing things, okay? And the way to do that is to introduce this concept called a primitive cell, which is the smallest unit that can be translated by integer numbers of these so-called primitive vectors, A and B. So A and B are vectors to replicate the entire lattice. What does that mean? Well, I can take this primitive cell ODEF, and I can translate that by integer number of these lattice vectors A and B, which are called R. So R is a vector, which is some integer number, say M times A, plus another integer N times B. That will put me in this location over here, right? Now, what's M and N in this particular example? We'll have to translate by 1, 2, 3. So it's 3 times A. And how many times B? 1, 2. 2 times B, right? So N is equal to 2 in this particular example. Now, clearly you can see that for different choices of these integers N and M, I can map out this entire lattice structure, right? So we'll see that to do mathematical problems, you don't have to worry about this entire lattice structure. You just focus on this most fundamental building block, the primitive cell, bounded by these primitive vectors A and B. And any calculation that you do based on that should give you the average value for the entire lattice. Okay. Now, one interesting point that you'll notice is, let's count the number of lattice points belonging to this primitive cell. Let's focus on this one. Okay. Now, in this particular example, I have 4 lattice points. Should I count this lattice point as entirely belonging to this primitive cell? Anybody? No.
No.
What fraction of that should count, do you think?
Are you referring to point E? I'm just making sure.
Yeah. Point E. What fraction counts towards this primitive cell?
1/4.
1/4. Very good, because it's shared between 4 adjoining primitive cells, right? Same with the other lattice points. And in fact, you'll see that in this particular example, 4 times 1/4 means 1 lattice point per primitive cell. And that's a fundamental theorem. So for all primitive cells, you'll only have 1 lattice point per primitive cell. Okay. Now, the way I've shown this is the primitive cells have lattice points only on the corners. That's just a matter of convention, okay? It doesn't really have to be drawn that way. You could just as well have drawn the primitive cell like so. As long as it has the right shape, and you have one lattice point per cell. But in our class, just to make life simple, we'll consider the drawing of the primitive cell with the lattice points at the corners. Okay. Now, one word of caution. These are the lattice points that I'm showing. Now, mind you, I told you that you could have a basis, which could be a single atom, but it could be a group of atoms. So I could have a more complicated structure where, say, maybe I have 3 atoms in the basis, okay? So I have an atom over here, maybe an atom over there, and another type of atom over here. And the 3 of these atoms form the basis associated with this lattice point. But if I do that, I have to do the same thing at every lattice point. So I have to put a plus type atom over here, a cross type atom over here, so on and so forth. And I have to do the same thing everywhere. If I did it in a slightly different way, so over here, if I put in, say, the cross over here and the plus over there, notice that has a different spatial arrangement of the atoms in the bases than over here. That would be an example of a crystalline defect, okay? So to make a single crystal, the basis has to be also put in the same spatial arrangement everywhere, okay? Now, a primitive cell, as I've told you, is not unique. In fact, you could have drawn a primitive cell like so also, as another example, okay? You'll see that it meets a definition that you can translate this by integer numbers of these lattice vectors. Now the lattice vectors are different. So this one is same as before, but this B is longer, right? Let me call it B prime. Okay, so there's really an infinite number of choices of primitive vectors that you can make, as long as it has the right shape where you can translate them by integer numbers of primitive vectors, and you have one lattice point per primitive vector. However, the convention is to choose the simplest possible primitive vector, which means I choose the shortest possible primitive vector and the next shortest, and that's the conventional choice. And that's what we'll be doing in this class. And the shortest and the next shortest will also give you the angle, which is the closest to 90 degrees. So here you notice that the angle is, much less than this angle over here. So that's the choice that we'll make, okay? One final comment, and then we'll stop. In this particular structure, I have chosen this arrangement of the points in this rhombus in a sneaky way, where you can see that I have this larger entity, PQRS, which is obviously larger than this primitive cell, because now if you count the number of lattice points, you'll get 4 times 1/4, plus you get the one in the middle. So now in this structure, PQRS, you get 4 times 1/4 plus the one in the middle. So you have 2 lattice points. So that's clearly not a primitive cell. But this structure is a rectangle, right? And in terms of doing math and stuff like that, it's obviously easier to deal with rectangles or squares or cubes rather than things like rhombuses and so on and so forth, okay? So it turns out in many cases in nature, this fundamental building block, the primitive cell, may be an oddball object, but you'll have a larger entity, which I call a unit cell, where I now relax my restrictions, where I allow lattice points not only at the corners, but if necessary, also in the middle of the face or in a 3-dimensional object in the middle of the body. And I do that only if this larger entity, the so-called unit cell, is a more geometric object, okay? And in this particular example, this rectangle is easier to handle than a rhombus. Now, what would happen if I shifted these atoms a little bit more, where this wasn't a rectangle, this was also a larger rhombus? Then there's no point dealing with the larger object, right? Because this larger rhombus is as hard to deal with as a smaller rhombus, right? So you only do that if you can pick a larger object, this unit cell, which is a more geometric object. And we'll see in the next class on Monday that in 3D, very often that's going to be the case, okay? So you have the simplest object, say the cube, simple cube, but in some cases, you are better off dealing with additional lattice points in the body center or additional lattice points in the square faces, so-called face-centered cubic. And this is the most important one because all our semiconductors have this kind of a crystal structure. All right. See you Monday. And once again, the lectures are recorded in the cloud. So if you want to watch it again, you can do that. All right.
Really quickly.
Yeah.
So like, let's just say for the body-centered cube, does that have like 5 points that it's connected to?
No, it's got 2 points. The 8 corner ones, only 1/8 of those count, because now I'm looking in 3D, plus the one in the body center counts fully. So that's got 2 points in it, okay?
Okay, so each dimension Like, so like the dimensions that they're in are counted separately?
So in 3D, say in 2D, we are looking at the 4 rhombuses, right?
Yeah,
But in 3D, you have to imagine a cube above that. There'll be 4 cubes in this plane, okay? And then 4 cubes in the next plane, right? So this lattice point will be shared amongst 8 cubes. So only 1/8 of those would count, okay? And there's 8 of those corner ones. So in the simple cubic case, 1/8 times 8 would give you 1 lattice point. In the body centered, 1/8 times 8, but the one in the middle counts completely, okay? So now you have 2. In the face centered, you have the 1/8 times 8 plus a 6, but now this are shared between 2 cubes. So you'll get 1/8 times 8 plus for the 6 face centered ones, half. So you'll get 4. I'll work out mathematical problems discussing this in great detail in the next class, okay? It'll become a lot more clear then.
okay.
All right.
Thank you.
I'll
Have a great
stay
day,
after.
Dr. Banerjee.
Yeah.
I'll stay after.
I have another class after this. So you can
Okay,
talk to me. Yeah.
Okay. I also have class after this. Okay. So I wanted to discuss accommodation.
Oh, okay. Yeah. The SSD? Sure.
Yes.
Okay.
Okay. So the only thing that's different than most students is having a formula.
Sorry.
I have a formula card.
Okay.
And since you allow us to have a formula card, sometimes in those cases, my professors allow me to have double that of the normal students, since I'm allowed
Double
to have
that?
it.
Sure. Yeah, that'll be fine.
Right. And like also like with the formula sheets, like let's say you're allowed an index card on the exam, some of my teachers will allow me to because I already have accommodation for
Sure.
a
That's
formula card. That's fine?
Yeah.
Okay. Perfect.
Right.
Thank you so much.
Yeah.
All right. Do you have any questions for me?
No, that's fine.
Okay,
Yeah.
perfect. Thank you very much. You have a great rest of your day.